Okay, so let's do it. Let's read some stuff first of all. So definition, let us consider the equations a1x plus b1y equal to 0 and a2x plus b2y equal to 0 and minus a1 upon b1 equal to y upon x. Okay. So we express this element as, right, so basically this expression a1 b2 minus a2 b1, that's what they are calling the determinant. So this is called the determinant of order 2. Its value is given by this thing. Okay, so that's the definition. I mean, it's not supposed to be like that. Determinant is supposed to be the area spanned by these two vectors a1 a2 and b1. I mean the vector a1 a2 and the vector b1 b2, the area spanned by those two vectors, that's supposed to be the determinant. Similarly, for three vectors it would be the volume, and that's why we write it as a triple product. It is a dot b cross c. B cross c is the area between b and c, right? And a dot, that thing, that just gives us the volume because it's a projection, right? The projection of a onto that b cross c vector. So it's like the height of the parallelepiped. So it's like a prism, if that makes sense, a slanted prism, right? Anyway, so in chapter exercise 1, let's do this. Oh, we don't want the answer key right now. The value of the determinant 131111324 is, yeah, so this should be doable. So let's see, 1 into 4 minus 2, that would be 2, then plus 1 into 3 into 4, so it's supposed to be like this, 2 4, and then you have a 3 1 over there, right? So it's a continuously repeating thing, but they don't write it like that. They just do a negative sign over there. I don't like to do that. So it should be 2 into 1 and minus 4 into 3. So yeah, so that's very much like 2 into 1 minus 3 into 4, something like this. So 2, this 2 thing is for the first, yeah, the first term, and then 1 into 2 minus 12, so minus 10. Okay, next 3 into 3 minus 1, 3 minus 1 is 2, so 3 into 2 would be 6. Okay, so 8 minus 2, that would be minus 2. Hopefully that's the answer. Okay, next question. If this determinant is 4, then the value of a is, okay, no big deal. So let's just do this thing, a plus 1 into, so 1 minus of minus 1, that would be 2. Okay, then I'll just do it like how they do it. Okay, so minus 1 into the down minus up thing, right? So I do it like up minus down. We can also do the opposite. Anyway, so minus 1 into this would be 0 anyway, so doesn't matter, plus 1 into this would be 2, right? So this will be 2a plus 2 plus 2, 2a plus 4 is given as 4. Oh, so a must be 0. Okay, let's see if that is correct or not. Most of the times whatever I do, it's always incorrect. Let's see. So b and d, yeah, it's correct. Okay, next question. Here are some more definitions. The minor of a given element of determinant is the determinant of the elements which remain after deleting the row and column in which the given element the given element stands. Okay, for example, the minor of a1 in, okay, right. So while calculating it, we first do this thing, right, and then we do something like the one with these things, and then so on. So those smaller determinants, 2 by 2 determinants that we solve for, those are called minors. Okay, also here's this negative thing over there. Okay, I get it. And yeah, okay, fine, I get it. So the cofactor is just negative 1 to the power of I plus j. I plus j, why do they have to put it like that? You know what, I don't think we will be having 4 degree determinants, 4 into 4 determinants or anything like that. because 3 into 3 are the most useful. Those represent vectors in 3D space. I don't know much about 4 into 4 vectors. How is that even like, okay, I get it that we could apply these rules for those as well. So in that case, it will be minus 1 I plus j. That's weird. I plus j. So all the stuff that's remaining. Okay, this is very not so good. Aij. So for example, if I was at a 1 2, hey, what are these I and j things though? A11 M11 minus A12. Oh, so this 1 is for the y coordinate, and this 1 2 and those. Okay, so these 1 2 3 are for the, wait, no, but over there what even is this? Okay, so these first numbers, they are for the x coordinate, and these are for the y coordinate. Okay, and over here the thing is something like this, right? So this would be the x coordinate, and this would be the y coordinate. Okay, that looks nice. So what they are saying is a11, which would be this thing, times m11. Okay. So for example, if I was at a21, right? So x coordinate is 2, and y coordinate is 1, so this would be this thing. So the minor for that thing, that would just be negative 1 to the power of 3, so negative of mij. Okay, fine. So mij would be the determinant with these things, so it would be a2 a3 c2 c3. This is a very complicated definition. Why do they have to define it like that? And then the cofactor is something like this. Okay, this is weird. What has this I plus j got to do with anything? I plus j. Well, okay, so maybe, oh, why think of I plus j? You can also think of it like negative 1 to the power of j minus I, right? That would also do. No, okay, wait. There must be something useful about it. And then these would be the cofactors. Okay, so this is good for well, at least for these things. Okay, fine. So at least for when you're doing this for just one particular column elements and one particular row elements, in that case it would just be some kind of alternating fashion, and the cornermost elements, they have this negative 1 to the thing, that thing as 1, so that's nice. Yeah, whatever. Okay, next, transpose of a determinant. The transpose of determinant is a determinant obtained after interchanging the rows and columns. Okay, cool. So this this column goes to the row. Fine. Symmetric, skew-symmetric, and asymmetric determinants. Determinant is symmetric if it is identical to its transpose. Okay. So we know that transpose and they have the same value, right? So you mean identical, like, oh, okay. So it looks the same. Okay, fine. For example, this determinant 1 1 1 1 1 1 1 1 1, its transpose would be, it would be the same thing, so that's why it would be symmetric. And skew symmetric is, what is this? A determinant is skew symmetric if it is identical to its transpose having sign of each element inverted. Okay, if all values of I and for all values of I and j. Okay, cool. Okay, so it's just, yeah, I get it. A skew symmetric determinant has all elements 0 in its principal diagonal. Okay, yeah, that's obvious, because if they were not 0, we could write like, if x is a element in the diagonal, then x equal to minus x, because if it's skew symmetric, its reflection along the diagonal, which would be when you take the transpose, right, it will just get mapped to wherever it was before, so it will still be the same thing, except that we want it to be negative, right? That's why it will be skew symmetric. So that means x equal to 0. So yeah, all the diagonal elements, they must be 0. Cool. Okay, next question. Properties of determinant. The value of a determinant remains unaltered if the row and column are interchanged. Yeah, I don't have a proof of this property. I think it's more or less algebraic, so we have to prove it with a lot of algebra. There isn't any way out of this. Fine. If any two rows or columns of a determinant be interchanged, okay, then the value of determinant is changed in sign. Yeah, so the determinant is not just the volume, it's also the signed volume. So you have to apply the right hand rule, and if the vectors fit perfectly, then it will, because the cross product, right? So the cross product, yeah, it's either along the one with which you will take the final dot product, or it's opposite to that, and so your sign will change appropriately. Cool. So that's nice. Yeah, next question, next property. If a determinant has all the elements 0 in any row or column, then its value is 0. Okay, yeah, so if one of the vectors is 0, its value is 0. So in row or column, it doesn't matter because the transpose is still the same thing. Okay, if a determinant has any two rows or columns identical, then its value is 0. That also makes sense. If two what was I saying? If two vectors, right, if out of those three vectors you take two vectors to be the same, or even if they are just collinear, yeah, that will be it. The not collinear, in fact, wait, what happens if they are collinear? Yeah, then the third vector taken in any kind of way, that, yeah, they will just form a plane. All those three vectors would be coplanar, so yeah, the determinant would be 0. So that's nice. So if they have the same value, the same vector value, that is, then cool. Or even if they are collinear, then too it will be 0. Okay, if a determinant has any two oh, this I already got. Okay, if all elements of any row be multiplied by the same number, then the determinant is multiplied by that number. Okay, oh, that makes sense, because it's, in the end, it's just a box product, right? So for example, if you had this thing k, a, b and c, then you could write this box product as k times a, b, c, right? Because basically it's something like this, right? Ka dot b cross c, and this ka, it's like k into c. Yeah, it's the same thing as that. Cool, that's nice. What else? If each element of any row or column can be expressed as sum of two terms, okay, determinant can be expressed as sum of two terms. Oh, so we can split determinants. The value determinant is not altered. Okay, fine. So why is that so? Right, this is not that bad, correct? So you can always change, you can always switch rows and columns and then switch them back. So negative, it will be positive once again, and when you switch it and then you do some operation and then switch it back, it's, yeah, that's basically what we can do. So we just have to prove this thing first of all. A plus a dash b c, this box product, this will be the same thing as abc plus a dash bc, and using this you can prove it for all these different rows, different columns. It will work, because just switch them and then use this property and then switch it back, right? So that's nice, and this property is obvious. Cool. Next, I don't want that. Okay, next, the value of a determinant is not altered by adding to the elements of any row. Okay, row or column, a constant multiple of the corresponding element of any other row, right? Okay, then d dash is equal to d. Wait, is that correct? I don't think this is. So this what's the proof for this thing? So we know that if two, yeah, okay, that makes sense. So for example, if you had this thing a1 a2 a3 plus something like k a1 or okay this k a2 and then then b1 plus k b2 or something like that. You know what, we need to write it in a better format. I can just write it like this maybe. Yeah, this is actually better. ABC, just write it like this. So convert rows to columns and then you can always write it like that. So what they are saying is that you can do a plus k times b and then b and then c, right? K times b or k times c or something like that. In fact, I just put k1b and k2c. Okay, cool. Then this thing can be written as apc plus k1 bbc, right? So split it and then take that k1 out plus k2 bbc, and then these are cbc, right? Cbc, and these will be 0 because two vectors are the same. So that's nice. So just leaving with this vector, but I don't think you can do it on two rows directly. Can you? So for example, if we did like this, a plus k1, why would this be true? I'll just try to. So when you split this thing ma2 mb2 mc2, it's collinear with this vector, so that will be 0, and then you can split this thing as well, the last row, and this na1, all that will be the same as that, so this will make sense. Okay, but what if we try to split this first? Yeah, it would be na1 and all that stuff, so it won't be directly, so we have to do it step by step and we cannot do it directly, right? There's a catch with this thing. Okay, I don't want that. So we cannot do it on two rows or two columns simultaneously, right? For example, I just take a to a. How will that turn out to be? That will just be abc plus k1. Okay, I don't want that, please. Okay, wait, not abc directly. I should just write b plus k2a c, then k1 k1b b plus k2a c, right? And then this will be a b c plus k2 a ac, okay, plus k1 b bc plus k1 k2. Wait, no, this is not making sense. bac, but what that would mean is that, okay, these are 0 but this thing is remaining. Yeah, what I thought was correct. We cannot do it simultaneously on both. Yeah, so they should have said that this is going to be step by step and we cannot do it simultaneously on both the rows or both the columns. Cool. Okay, fine. Examples, yeah, I will skip that. Use of factor theorem to find the value of the determinant. If by putting x equal to a, the value of what x equal to, I don't get it. Oh, okay, so for example, if like if x was one of the elements or something like this. Fine. So let's look at the example first. Putting a equal to b, you get determinant as 0. Okay, hence a minus b is a factor of the determinant. Oh, so consider this as a function of a, right. So they are considering this, so instead of saying a, I'll just say x, right? So now it's more clear why that should be the thing, that yeah, when you put x equal to b, this will just turn out to be 0. Yes, that's correct, that is correct. Okay, that's nice. What else? Oh, where did you go? Okay, fine, so that's okay. And then what? Similarly, a minus b minus c minus a is a factor of determinant, but the given determinant is having degree 5. Wait, how can you tell what the degree is? Okay. Not bad, because degree of these this thing and then that thing both have the same degree, and then all of these things have the same degree, so it will in fact be a degree 5 kind of thing. Okay, so this degree is for a, b, c, all of them, not just for a. Fine. Since this is an identity, so in order to find the value of lambda and mu, so you will just put numbers inside and get the value. So get two equations and then that will give us the value. Okay, fine. Okay, in chapter exercises. So let's try it. The value of the determinant a1, a2, a3, m a1, it's going to be 0. Look at this. This is collinear with that. It is definitely 0. The value of, right, so you will just have to split this thing, right? So when you will split this, this is going to be collinear with that, so that will get erased, and the other thing will be remaining. The other determinant didn't get erased, and then this is actually collinear with that, so it's also, this is obvious. The third vector is just a linear combination of the two vectors over there. Yeah, they are coplanar. It's going to be 0. If this thing is 0, then the value of x r. Okay, so when is this 0? That's what they're asking. A plus x, a plus x, a minus x, a minus x, a minus x. So that's nice. Then the value of x r. How can you do this if this determinant is 0? Okay, so a, for example, okay, so if is 0 for example, then no, then it won't be 0. I don't think 0 will work. No, when you put 0 in this, it is going to be a everywhere, so this will be a times this. No, actually it does work. When you put 0 over there, all of the columns become equal, so that will be giving us 0. So 0 is definitely one of the solutions. What else can we do? So can we put a over there? That will give us 0 over there. These will be gone, and then you will just have, no, that will give us a power 6, because it will be something like an identity matrix but multiplied by a squared, right? So that will be like a power 6 will be its determinant. Fine. So no, a doesn't work. Minus a, maybe, and 3a, that was like 4 minus 2. So that we have to find out ourselves. This is so problematic. Okay, so 0 works, that's what they are saying. Value of x r, x equal to 0 works, right? So we can just write this determinant as x times something. What will that something be? What's the degree of this determinant? Degree of this term is 1, then the degree of the multiplication of these two will be Okay, that will be squared, and then this is also squared. Oh wait, but if you do that, that won't be nice. Nah, it's okay, it's okay. When you multiply these, for example, that will be a positive x square, and then minus of minus x square 2x square. So yes, it's a 3-degree polynomial. So it's gonna be some kind of quadratic over there. So there are going to be 2 more roots. Should I just solve this like, no, that's not correct. Maybe I should though. 0 works, and what else works? I guess maybe x minus a x plus a. Nah, if that was the case, then both of these would be true at the same time. You know what? Let it be. I'll just solve this. I'll just manually solve this. Sometimes that's the best way. Oh wait. Why didn't I think of it like this? Oh, we can do much better than that. We can do so much better. We can just write it like this: a minus x, a plus x, a minus x. Wow, this is really a useful property. And then plus 3x is over there, and then a minus x, a plus x, and a minus x. And yeah, that's nice. So here's the thing, this is really useful. Whenever you will split one of these, right, so you will write as a and minus x, you will split that thing out. It's supposed to be minus over there. Okay, cool. So whenever, for example, let's do for the first determinant, whenever you will split that thing out, the one with a as a row or column, a row basically in this case, that will get that will get cancelled, because that will be 0. The determinant of that thing, that will be 0. So we can just erase this thing, right? Does that make sense? When you will split this, that a thing, that will be identical to the first row, so it will get 0. It will become 0, and the remaining thing will be there. Okay, so this will become 0 as well. Oh wait, this is plus over there, that's minus over there. Yeah, fine. Okay, cool. So that will just become 0 directly. That's nice. You can do some similar thing for this as well. You can first of all remove these things, and then it will be x minus x and minus x plus x minus x. Okay, wait, what? No, it's supposed to be minus over there. This is supposed to be minus over there. Fine. And a minus x plus x. Okay, and then with this a, you can just remove that as well. So that's nice. That is nice. Cool. And then what? And then what? Think. These are definitely much more solvable, but it's still something that, come on, think. Just keep on thinking. You would want to break that as well. Okay, we really need to, maybe this is not the best way to do it. Maybe you should have just multiplied it, but whatever, we'll just write it as 3 different determinants, and hopefully that's, in fact we can also write it as 4 different determinants, right? One with all the x stuff, so this will be x minus x minus x minus x plus x minus x minus x minus x plus x. Okay, oh come on, think. Oh, so maybe we can actually derive a full identity from this thing. Oops. So this is of the format something like this: a1 a2 a3 plus something, so h for example, plus h, and b1 b2 b3 plus h plus h plus h, and then c1 c2 c3 plus h plus h plus h, right? That's what it is like. So now how do you do this? Think this is like a vector plus, call this vector as h vector dot a vector, sorry, b vector plus h vector cross c vector plus h vector. Maybe that's better. So a dot, okay, a plus h. Let's look at what this will be. It will be h cross h plus h cross c plus b cross h, okay, right? B cross h plus b cross c. Cool. Now put that inside it, so this will be a dot over there, a dot h cross h is 0, so we don't have to worry about that. This will be h cross c plus b cross h plus b cross c, and then plus h dot all that stuff. So these will get zeroed anyway because they are perpendicular to h, so it will just be h dot b cross c. This is a nice thing, right? Okay, so what will it be like? It will be a h c plus a b h plus a b c plus h b c, and we don't want it like that, we want in a better format. So I will write it like this. It will be first this thing h b c, okay. Oh wait, so this is actually nice. This is not bad, not bad. So you see ABC over there. Instead of B, put H over there. Instead of A, put H over there. Instead of C, put H over there. So you can go from this to these three things by replacing ABC by H. So that's a nice identity. So we can use that to simplify a lot of things, right? So you will first of all only have this determinant x minus x minus x minus x plus x minus x. Why even write it like that? Write it like this. Wow, this is super useful. X cubed 1 minus 1 minus 1 minus 1 1 minus 1 and minus 1 minus 1 1. Okay, we will find out what this determinant is, and that will be easy to find. Okay, we also want these three things, so it will be plus the determinant. Okay, so let's just take that x square out anyway. Okay, and now you will just have these replaced by h. Okay, cool. So this will be 1 minus 1 minus 1, and a, you know what, take that out as well. Ax squared, cool, 1 1 1, and over there it will just be minus 1 minus 1 1. That's also nice. And plus ax square once again. Wow, this is really nice. So there are going to be 3 of these, right? So we will take 1 1 1 and then replace these by that. So minus 1 1 minus 1 minus 1 minus 1 1 plus ax squared. So notice there are no x terms over there. Isn't that weird? How did that happen? We don't know, but that did happen. That's a nice thing. So this is going to be minus 1, sorry, not 1 minus 1 minus 1, and now the last one will be replaced by this 1 1 1 thing, and this will be minus 1 1 minus 1. I know I'm making it really long, but this is a nice thing. We discovered something new. So we can use this thing to have polynomials generated. Okay, and now we can just find what this is supposed to be, right? Cool. Okay, okay, now let's find out what this is. uh you know what, forget that, we can do better than this. Add and subtract things over there, that will also do something, right? So you will add 1 1 1 over there and make it 0 0 0, and over there it will be 2, and then you will once again do that but on this side, so it will be 0 0 and it will be 2, and then over here we cannot do anything, it looks like that, right? Still we can try to subtract on the, no, we will solve this by itself, but okay, cool. And what about this thing though? Yeah, do the same thing over there. This will be gone, this will be gone, all of these will be gone, and this will be converted to 2 and 2, 0 0 0 0. This is a nice thing, this is really nice. 2 0 0 0 0 2. That was fun. Okay, and now we can solve this. I think first maybe we should memorize what this determinant is, because it is going to come a lot, because this looks symmetric and stuff, right? So this determinant 1 minus 1 minus 1 minus 1 minus 1 1 1 plus 1. All of these replaced by minus 1 of it. What will this be? This determinant, think, whatever, just find this out. 1 into 2, no, into 0, sorry, into 0. Okay, then plus 1 into minus 1 minus, okay, minus 1 as well over there, fine. Minus 1 into 1 plus 1. Okay, that is the thing. Cool. So it will just be minus 2, which is minus 4. So this determinant is minus 4. So what that means is that this determinant, minus 1 minus 1 minus 1, and everything else is covered by 1. This will in fact be plus 4. Maybe this will be useful somewhere. Anyway, so all we really care about is the fact that this is going to be 4x cubed. And then we can find out what this is supposed to be, right? Okay, so this will be like minus, yeah, whatever, just solve this, man, just solve this. So 2 into 1 into 2, that will be 2, so 4, okay, then 1, and then, oh, these are going to be 0, and then 0, and that's going to be 0 as well. Oh, this was nice and really small. So it will be 4ax squared. And then what about this thing? Similarly, 1 and 2 into 2, 4, and I think everything else will be the same. 0 0, those will be gone. Cool. So it will just be 4 over there, fine. So it will be 4, and this final determinant, that will also be 4. Yeah, just transpose this and cool, that will also be 4. So this was just 4 times x cubed plus ax squared plus, okay, 3x squared. So it will be 4x squared into x plus 3a. So minus 3a would be the only other solution. Cool. That's nice, right? Oh no, this should be minus 4. This should be minus 4 over there. Yeah, that's nice. So this will be minus x over there. So 3a would be the other solution. So 4x squared and 3a minus x. Cool. So 0 and 3a. Go to the next question. One factor of this thing is, so we got abc, a squared, b squared, c squared, 1 plus all that, right? So you can split it. It will be abc a square b square c square, a cube b cube c cube, right? Cool. And yeah, fine, that's nice, that's nice. Oh, we can write right, and plus abc a square b square c square 1 1 1. Cool. So we can just take out abc from this. So this will be abc, right? 1, because yes, this complete row is multiplied by a, so we can take that out. So 1a squared, sorry, 1a squared, 1a, sorry, 1bb squared, and 1cc squared. So abc plus 1 would definitely be a factor. That was nice, it was easy. The value of the determinant is, okay, fine. So you can first of all just take that k out, so k times the determinant, and then you can split it. So it will be abc a squared b squared c squared 1 1 1. Cool. Plus, oh, we can also, so the other one will be abc k squared k squared. This is going to be 0. K squared k squared, that's whole linear with 1 1 1, so that's 0. So the value determinant will be this thing. Okay, so k, yes, so we can also write it like this, transpose it, right? So abc a squared b squared c squared 1 1 1, and shift it like this. First of all, switch these two, and then switch, so you just get minus k 1 1 1 a squared b squared c squared abc, and then switch these two. So k into abc, oops, sorry, k into 1 1 1 abc a squared b squared c squared. That's nice, that's really nice. So this will be k into bc squared minus b squared c plus a squared c minus ac squared plus ab squared minus bc squared. Cool. And that looks correct. Fine. So you got ab squared first, then you got bc squared, then you got ca squared. This looks correct. So what did we have to find? The value of this determinant is, so this will just be k into, take that bc out. No, don't do it. Maybe that's not the best way of doing it though. Do you really want to factor that out first? So take that b squared out first of all. So like taking that b squared out would be a minus c plus, no, this is not the best way. So maybe some other way that we could use. First of all, write all the positive terms, bc squared plus ab squared plus ac squared. Oh wait, this was b squared c, that is not there, that's not there, right? There was no bc squared thing, c squared. Now what? You just have to use factor theorem. Okay, fine. So for example, if you put a equal to b, right, if you put a equal to b, then yes, it will be gone. So a, taking it as a function of a, you will have a minus b as a factor. Then similarly, you will also have b minus c and all that stuff. Cool. So taking it as a factor of b, you will also have b minus c as a factor, and b minus a is also a factor. And then taking it as a function of c, you will have c minus a as a factor. Cool. That's nice. Fine. And if we like some multiple of that, what will that multiple be? What will that multiple be? Oh god. Now what? What is this guy's degree? This has the degree 3, and over there you also have 3, so it will just be some constant over there. Well, anyway, it will just be this thing. Cool. Yeah, hopefully it will be symmetric and stuff, so it will be 1. Next question. If x is not equal to y is not equal to z and this determinant is 0, then the value of x, y, z will be x is not equal to y. First of all, just write it like this. 1 1 1. So you can always switch this like that and then like that. So 1 1 1 x y z, x square y square z square. Cool. Then plus, when you take that x cube y cube z cube over there, you yes, actually that's already in the format, so just take x y z common, and it will be 1 1 1 x y z, x square y square z square. Cool. Then the value of x y z is, oh, so x is not equal to y is not equal to z. Cool. Then all of these vectors are different, so the only remaining option is that 1 plus x y z, that has to be 0, so x y z has to be -1. Next question. Find the value of determinant a minus b minus a, c minus. Okay, fine. Come on, think. This is in some weird order. Minus a, c minus a. This is like a skew symmetric determinant. Huh. Hey, wait. We know that a skew symmetric determinant has the, yeah, so when we will transpose this thing, oh, we could have, wow, I am stupid. Why didn't we do it like that? We could have just transposed it altogether. But anyway, for at least for this determinant, transpose it, so we'll just get this determinant over there, 0 0 0 a minus b and then b minus a. That's also the same thing, right? So delta is also this thing, so 2 delta, wait, so just all of these multiplied by -1, right? Yeah, all the elements are just negated, so it will just be negative of that determinant, right? So -1 cube, I should say, but in the end it's -1, so it's actually negative determinant is 0. Fine, so this value is 0. Simplify this thing, b square minus ab. Okay, wow, b square minus ab minus a square. What one is this? Oh, hey, first of all, look over there. We can write it like this: b into b minus a into b minus a, and then c into b minus a, and all the other stuff. So you can just take that b minus a out. Similarly, you can also take some other stuff out, right? So from the third column, you can take, let us see, you can also take b minus a out, right? Yes, it also has b minus a multiplied everywhere, so take that out. So the inside stuff that will be remaining is so over there you just have b, over there you have a, over there you have c. This will be b minus c, a minus b, and c minus a, and this will be, oh, I think it's going to be 0. C, b, a, yeah, it's 0. This is a linear combination of the column 1, column 3 vectors, so it's 0. Simplified, it is 0. Cool. Yes, I'm pretty sure that's the thing. Next question. We don't want the answer key. Okay, prove that this is that. Oh well, maybe we can actually transpose and stuff out here. Okay, what if we do that? That will be 0 0 0 everywhere. No, that would be 0. That's stupid. A plus b plus c cube. Okay. Think. You can always do that thing, but that's not really useful. What about try to add and subtract? Yeah, that might work. Just might work. 2c over there, and that would just be b plus c minus a. Let's try it. First of all, let's try adding the last row to the first row. That will be 2 times of b plus c over there, and over there it will be b plus c minus a, right? And then over there it will be we need more space, so the second row, that will be c plus b minus a, and then 2c c minus a minus b, cool. And then the first, it's just the same thing. Okay, this was not that bad. So now add row 1 to the new row to that you have. So it will just be a minus b minus c, 2a. When you add this, it will just be a. Yes, that's correct. A, and then plus b plus c, and then this will also be a plus b plus c, and this will also be a plus b plus c. So that's why you're getting cube. So we can manipulate this to get something nice, I think. Okay, 2c c minus a minus b. So just take that out. This row is completely multiplied by that thing, so it should be a plus b plus c times the determinant. In fact, wait, maybe we can do it better than that. For example, if we add this over there, that will be a minus b, and okay, this is not the thing. Think this thing times a minus b minus c, 2a. Oh, it should be 1 1 1. Yes, it's going to be the thing. So we don't want to disturb that. Cool. And then you will just have 2c and c minus a minus b. Let's try it. Let's try adding the thing. So it should be a plus b plus c. So add this to that, right? Yes, that will be a plus c minus b, and then we need more space constantly. A plus b plus c is there, right? That factor is there, and other than that you have the determinant. Add that, so a plus c minus b, 2 times of a plus c. Okay, a plus c minus b once again, fine. 1 1 1, 2c c minus a minus b over there, fine. Okay, and then what? And then, oh come on, think. Oh wait, you can do that, right? So why not maybe we can a plus b plus c. That's what we actually will need to, yeah, yes, that will be nice. C minus a minus b. And that will be 3c over there. That's not going to work. What should we do? We got a plus c and then minus b, and now what am I supposed to do with this thing? I don't know. Maybe we should just solve that at this point, right? It looks good enough to be solved directly, I think. Yeah, right? Or is there something else that we can do? No, I don't think we can do anything. We have to manipulate these rows to get something out, but it's so not good to do that. So we really just want that this times that give us something like that. No, no, that won't happen. It just won't. Oh wait, why didn't I think of that first? Okay, so divide this thing by 2b and multiply this thing by 2b everywhere. That's nice, that's nice. So it will be a plus b plus c upon 2b, and now for this determinant add this thing to that and also to that, right? So you can do it stepwise. So this will be actually add this to that and then add this to that as well. Okay, that will probably give us nice things. Okay, so doing that you will just get a plus b plus c, and over there you just get 2 times of a plus b plus c. Wait, 2 times of uh we don't want 2 times though, that's not correct. And then what? Okay, so you'll get 2 times of a plus b plus c, and over there you will get yeah, once again just a plus b plus c over there. So it will be square of this thing, and you will just have 1 to 1 1 2 plus 1 over there. It will be square of that. Why did it even do this 2b thing? We could have just multiplied. Yeah, so we can always add multiples of rows to that, right? So once you got this 1 1 1 thing, you could have just done this thing. Cool. And then similarly, uh, let's say multiply this complete thing by 2a and then add row 1 and row 2 to row 3. Yes, that is possible. So that will just give us a nice result. Yes, that will give us 1 to 1 over there, and this thing will be cubed. And what is this thing now? Or you can just subtract some stuff over there. So a plus b plus c cubed, subtract some stuff out. Oh, wait, no, this is not right. This is not right. If this is 1 1 1 and this is also, that would be 0. That is not nice. This is not supposed to be 0. This is, why am I writing this plus over there? No, this is it. Oops. Okay, not supposed to. You would get 2 over there. It's not nice. So 2a won't work. What about 2b? If I add 2b over there, and this will be 2b over there as well. As we see. Oh, we cannot do that, right? So once we replace this thing by 1 to 1, after that point we cannot do that kind of problematic things. Oh shit, that's not, what did I do? Okay, so this is entirely incorrect. We cannot do that step. So what can we do? We need to do something to get that out. I mean, at this point we can just kind of already calculate this thing, but still, any other nice way to do it, to get a plus b plus c somehow? I mean, if you have 2c over there, this would be good if you just got like minus c. Okay, that is something. Minus c, fine. And then what? That minus c probably won't work, so it should just be a plus b over there. Come on, think. That would be c over there. Okay, minus 2, that would be gone, and that would just be minus a and b. No, it won't work. It just won't work. Oh, what am I even thinking? Just add 2 times of a plus b. Right. So we can multiply this R2 row by 2 times of a plus b plus c, right? No, 2 times of a plus b. Yes, 2 times of a plus b, and then add to this thing, and yeah, that will give us something nice. That will just give us a plus b plus c cube, and then 1 1 1, sorry, 1 2 1 1 1 1, and this will be 2 2 1. Yes, yes, that's nice. And this is not 0. Cool. And then what? Then subtract this thing from that. So a plus b plus c cube, 0 1 0 1 1 1 1 1 0. Subtract once again, so a plus b plus c cube, 0 1 0. Subtract this from that. Yes, that is doable at least. Cool. So that will just be 0 0 1 and 1 1 0 over there. Cool. And then subtract this from that, so this will just be 1 over there, and this will be 0. Cool. That is the final matrix, that final determinant that we will get. So now if I try to, oh yeah, this is actually just 1, right? You can switch columns twice, and that will give us the result that we were wanting. Yes, that's nice. So switch these two columns first, and then once you get that first column into the second column, switch these two columns. That will give us 1 as a determinant. So it will be a plus b plus c cube. So yes, we proved that. Fine. Show that this thing is a minus b by using factor theorem. Yeah, factor theorem. Cool. So for example, when you just put a equal to b, what do you get? You just get 1 1 1 b b c, and b c, a equal to b over there, b c, and b squared. So you can just take that b out, so it will be, and this will be gone. Yeah. Oh, these are in fact coplanar, right? Just add these two rows and divide by b plus c. That will give us 1 1 1. So these are coplanar. Then that would just be 0, right? So that's nice. Yes. So that means a minus b is a factor, and then because it's so symmetric, do the same thing for c as well. Just put a equal to c, it will also give it the same thing, and then put b equal to c, it will give us the same thing. So yes, it's pretty much doable. Okay, let's check. So 1 a, yes, second b, yes, third b, fourth c, fifth c, yes, sixth also c, seventh 0, yes, eighth 0, ninth and 10th are proof that kind of questions. So okay, multiplication of two determinants, right. So it's like applying two matrices, so multiplication of that matrix and determinant of that final matrix. Yeah, I'm used to this stuff. Cool. So let's go to next thing, summation of determinants. Okay, so you can do this for one row. Yeah, cool. Okay, it's not bad, it's doable. Okay, so only one row or column. None of the elements other than that row or column should be dependent on R. If more than one column or row have elements dependent on R, then first expand determinant and then find the summation. Right? Doable, not bad. Okay, examples. Cramer's rule, system of linear equations. Consistent equation, definite and unique solution, intersecting lines. Inconsistent equation, no solution. Okay, let me A1 1A2 is not equal to B1 consistent. Inconsistent. Okay, that's not a big problem for 3 variables. So for 3 variables, x is d1 upon d, d2 upon d, and then y, z is d3 upon d. Huh. What is this d1, d2, d3? So it's these. Okay, fine. Okay, not bad. Come on, think. How is this going to be? If you have x, y, z as a vector, and then you take that transformation over there, right? And you get d1, d2, d3 as the vector. So how do you find what x, y, and z should be? Okay, think. There must be something that we have to extend that vectors. We will have to prove that after all of this, but really d1 is just d1, d2, d3. Why is that the thing? Determinant is supposed to give us a volume. b1, b2, b3. So the vectors are remaining. Sorry. So like think about it like this. For example, the equation that we are dealing with is this matrix equation: a1, a2, a3, b1, b2, b3, c1, c2, c3, right? Times x, y, z. That is this vector d1, d2, d3. Okay, and then what? So the volume of wait, something's weird. This determinant is supposed to give us the volume, right? It gives us the volume change. Okay, so for example, if you consider x, y, and z, right, just consider x I hat, y j hat, and z k hat, the volume between these vectors, right, that times its determinant, that would just, okay, fine. And this is this new okay. The volume of that thing will just be d1, d2, d3. So that's the first equation that you have: x, y, z times the determinant. Let's call this d. That will be d1, d2, d3. Okay, no big deal with that. What is these what are these things though? d1, d2, d3, the volume of that thing with b1, b2, b3, and c. What? Why? Okay, let's just, this is not sufficient space. We need to think about this. So just consider vectors. For example, consider the vector abc and xyz. Xyz is like, yeah, xyz are scalars, right? So x a vector plus y b vector plus z c vector equal to this final d vector, that's d1, d2, d3, right? That is the thing. And what we are seeing is that the solution for this equation is x equal to the box. So d1 is this thing, d b c upon the box abc. Why? Oh, this might make sense. So just multiply, okay, consider this thing. Take dot product on both sides with b cross c. That will give us d1 on the right hand side at least. And what about these things though? This vector is perpendicular to b and c, so when you take the dot product of that with the b vector, that will be 0. So you will just have, and similarly for C it will be 0. So you'll just have x a dot b cross C equal to, yeah, that's nice. That is a really easy way to get this. Oh, so that makes sense. So whenever you want to solve equation like this, just consider taking the dot product with b cross C, and that will give us the thing, right? So it is really this thing, dbc upon abc, that will give us the value of x. And similarly for yes, for y you would just take DAC and BAC and so on. Yes, that's nice. That is nice. So D2 vector you said would be this thing, ADC. Okay. So yes, this makes sense. So whatever you do on the top vector, if you do the same thing on the bottom vector, the signs will cancel, right? So for example, if I shift this, it will be ADC but negative, and then if I shift that, it will be ABC and negative. These negative signs will cancel anyway, so you can do it without any worry. And similarly for D3 as well. Cool. So yeah, similarly for Z. This is nice. This is really nice. Cool. Next question. Consistency of a system of equations. If D is not equal to 0 and at least one of D1, D2, D3 are not equal to 0, then the given equation of system are consistent and have unique non-trivial solution. So if D is not equal to 0, at least one of these are not 0, have a non-trivial solution. Okay, cool. Yes, that makes sense. If D, so yes, this is obvious because wait. That is one of them. So what happens if all D1, D2, D3 are like 0? Then you would just have x equal to y equal to z equal to 0. So what's bad in that? There's no problem, right? Why is that a non-trivial solution? You would just have x, y and z both all be 0. So then D will be 0. Yeah, D will be 0. Oh, okay. So if for example D is 0 and no, that's not correct. 3 variables not cool. Not 3 variables, that will be non-trivial solution. When will this exist? So that will basically be giving us something like this, that if x, y, z all be 0, then you would have something like ax plus by plus cz equal to 0. So yes, this equation has a trivial solution, x equal to y equal to z. Why am I doing this? B and then c over there. Fine. So x equal to y equal to c, z equal to 0. There would also be a non-trivial solution if these are coplanar, right? So if a, b, c are coplanar vectors, then there would also be a non-trivial solution. So that's what this guy is talking about. Anyway, if d equal to d1, d2 equal to d3, then this given system of equation have either infinite solutions or no solutions. Okay. So if all of these are 0, when does that happen? That happens when ABC are coplanar, ADC are coplanar. So like D is in the plane of ABC, right? ABC is a plane and D is also a vector in that plane. Oh, it will have infinite solutions or no solutions. Yeah, whatever, we won't be talking about that right now. If D is equal to 0 but at least one of D1, D2, D3 is not 0, then the equation are inconsistent and have no solution. I mean, okay, if D is 0, then you have problematic things. If D is not 0, then okay, whatever, right? So if D is 0, you can only go into a particular plane And if d1 is so right, if d a d vector that does not lie in the ABC plane, and that's a problematic thing because we cannot reach that d vector because we can only roam in the plane, and that means there will be no solution. Okay, so this d condition I get. What about the c condition? This is weird. You're saying that if all of these are 0, then there are infinite solutions. I mean, you're not wrong. You're not wrong. Because if all of them are in a plane and it's a 3 variable system, just consider one of them to be some constant and then transpose that. For example, if we have a plus b plus, sorry, x, y. So just consider z to be some kind of constant and then send this to be there. Yes. Yeah. Yeah, right. Cool. And then you know that this thing is still in the plane of ABC, so you can always write it like this. So there will be solution to x and y. Cool. But you can choose any kind of z naught that you want, which means there will be infinite possibilities for z naught and all of them will have solutions. So there will be infinite solutions, right? Yes, actually that looks something like, well, no, not like that. Okay, whatever. Next question. Three equations in two variables. If x and y are not 0, then the condition for to be consistent in x and y is determinant must be 0. Okay. Yes, that makes sense. Just consider, yes. It would be something like this: a bar x plus e bar y plus c bar equal to 0. That's the equation that you're considering. Yeah, something like that. Think about it, bro. That c bar over there, I mean, yes, in effect that is the equation that you're considering. So when will this have a solution? Yeah, when these will be coplanar. So that's nice. Okay, not bad. Next question. All of these are examples. Application of determinants. Following examples of shorthand writing large expression are: area of triangle whose vertices are given is okay. If d equal to 0, then the 3 points are collinear, right? Do you really need to do that? If you know all the 3 vertices, just take one of them to be the reference point and then find the cross product of the vectors that you will get and take half of them. That will be the area, the signed area. Yes, but you can always take the mod of that thing. So this is stupid. So this one thing that just represents the fact that the z vector, right, that's 1. Yes. So this should be something like this. The vectors that we're talking about is x1, y1, 1, x2, y2, 1, and x3, y3, 1. The volume between these vectors, that is just, yeah, that's the thing. Not bad. This is a nice way of representing it, but still it's not useful. So the thing for this is, you're just considering 3 vectors: x1, y1, 1, x2, y2, 1, and x3, y3, 1, right? And you're finding the volume enclosed by these 3 vectors. Yes. Yeah, that's what we're doing. Volume enclosed by those vectors. But we know that wait, yes, because this last vector is 1 over there. That's why we have that thing. Does that make sense? Okay, it is volume, but one of the things, the height of that thing is 1. Maybe that's why we're doing this. Okay, so just think about 3 points and think about the 0 over there. These 3 points are height 1 away, right? So this complete plane is just height 1 away from the origin. So if I take this distance, right, this would be 1. So what does that mean? The parallelogram, the parallelepiped, that will be, one thing about it. Yes, the parallelepiped will have the following. It will just be, yes, that makes sense. Right, it just starts to make sense now. Yeah, nice. So this will be something like the parallelepiped over there. Cool. Half of that volume will be this thing. Yes, and yeah, that must be the thing. It must be the thing. It is something like a tetrahedron. Wait, but if it's a tetrahedron, then it should be like not half the volume. It should be 1/6 the volume, right? The parallelepiped will be something like this. All of these are parallel to that. Right. Is that correct? I think that's correct. Yes, that's nice. Okay, and we just want the tetrahedron over there. Yeah, so not the tetrahedron. In fact, we don't want the tetrahedron at all. Yes, this is doable. The volume of the tetrahedron will just be 1/6 uh 1/6 of the volume of this parallelepiped, which is the determinant, right? 1/6 the determinant is the volume, but the volume at the same time is also the area of his triangle. Because it's something like a pyramid, it will be 1/3 the height is 1 over there, because yes, this is just, we set it to be 1, so 1/3 into 1 into the base area, which is what we want to find. So our area will just be 1/2 the determinant. Nice. So this was nice. Next question, next whatever the thing is in chapter exercise 3. Okay, so tr is this thing, then the summation from r equal to 1 to n. So notice that only this column is dependent on r, so we can do that summation thing, right? So it will be the summation from r equals to 1 to n of r, summation from r equal to 1 to n of 2r minus 1, and summation from r equal to 1 to n of 3r minus 2, right? And all other stuff over there. Let's just find out what this thing is. It's going to be n into n plus 1 upon 2. What about this thing? It's just odd numbers, so first n odd numbers, that will be n squared. What about this thing? It will be minus 2 plus 3 into n plus 1 upon 2. Maybe I should just write it as n squared plus n upon 2. So this will be 3n squared plus 3n minus 4 upon 2. Okay, which maybe is factorizable. Is it? Wait. Sorry. Where was I? Oh wait, so this minus 2, it will also get summed up, right? So it will be minus 2n over there. So this will be minus 4n, so this will be minus n. So n into 3n minus 1 upon 2. And guess what? It's exactly what this third column is. Where is it? Yes. So this will just be 0. Next question. Evaluate summation from r equal to 1 to n dr if dr is this thing. So once again, only these are dependent, right? So summation from r equal to 1 to n. Okay, r minus 1, then r minus 1 squared, then r minus, so it's like first element that you are talking about is summation from r minus 1 is 0, so k equal to 0 to k equal to r minus 1 will be n minus 1, right, of k. So this thing will just be n minus 1 plus 1, which is n into n minus 1 upon 2. Cool. The other thing is r minus 1 squared over there. What will that be? That will be like summation of k squared from r equal to k equal to 0 all the way till k equal to n minus 1. Fine. So that will be n minus 1 into, so it's supposed to be 2n plus 1, or then first n plus 1, so into n and then 2n plus 1, so 2 minus 2 plus 1, 2 minus 1 over there upon 6. Cool. Right. And yeah, anything else over there? All of these will have that n over there, so we can just take that n out. And the third one, from k equals to 0 to k equal to n minus 1 k cube, that will just be the square of this thing, so n to n minus 1 upon, this is supposed to be 2 squared, so this squared upon 4. Yes, that's correct. So just take that n out, then this will be, in fact take n into n minus 1 out. Cool. Then it will be, you will just first of all have 1 by 2, then 2n minus 1 upon 3, sorry, 2n minus 1 upon 6, and n into n minus 1 upon 4. In fact take that 2 out as well, so take that out, so it's be 1/3 over there. Cool. And over there will just be 2. Fine. You know what, whatever, take something more out. Take 12 out from this thing, so multiply by 6 everywhere. It will be 6, it will be 3 times that, it will be wait. Oh, it will be 2 times of that. Okay, cool. So it will be 2 into that, it will be 3 into that, it will be 6 over there, so upon 12, n into n minus 1 upon 12, 6, 4. This is going to be the same thing as previous question, 3n squared minus 3n. Yes, it's 0. It is 0. Next question, solve the following system of equations. So you have the following 1 2 wait sorry, 1 2 3 2 3 4 3 4 5 xyz, that is 1 2 3. Okay, that's the equation, and you want to solve this. So our x will just be d1, which would be the determinant where you're replacing a by d, so 1 2 3 2 3 4 3 4 5 upon the one with that thing. So actually just calculate everything. d1 is going to be this thing. Oops. 1 2 3 2 3 4 3 4 5. I'm getting a bad feeling about this because 1 2 3 2 3 4 3 4 5, all of these are just consecutive, right? Yeah, these are coplanar. Yes. Yeah, well, looks like that. These will be coplanar. Look at this. This is an AP, right? 1 2 3. So if I do R1 plus R2 minus 2 times of the R1 plus R2 minus 2 times of R3, that will be 0. Wait, what that means is that D is in fact 0. So one of these equations is just redundant. Yes. Which one? This one. The one with R2. That was, oh, that's not nice. This is a redundant wait, what? Okay, just add the first and last equation. That will be 4x plus 6y plus 8z equal to 4. Just take half of that. It should be 2x plus 3y plus 4z equal to 2. This equation is not useful. So just these two equations, which will in fact have infinite solutions. Yeah, that will be the thing. So it will have infinite solutions. How am I supposed to solve this? Infinite solutions. Next question. Yes, that's correct. Solve the following system of equations. Let's check if one of them is redundant as well. 1 minus 1 minus 1 over here. 1 2 3 2 3 4. So that would give me 1 1 1. No, it's not redundant. Fine. So just got 1 2 3 2 3 4. 1 minus 1 minus 1 times x y z, and all of them are 0. That is stupid. All of them are 0. Wait, then that means d1 d2 d3, those are 0 as well. Okay, and this determinant is not 0, so oh, that means only 0 0 0. That's the only solution for this thing. So that is the thing: x equal to 0, y equal to 0, z equal to 0. Next question. I don't want to see the answer. Solve b plus c into y plus z minus ax equal to b minus c. Okay, how many equations do you have? We don't want that. This is 1 equal to sine. This is 2 equations. And that's 3 equations. Oh, this is going to be not good. B plus c into y plus z minus ax equal to b minus c. Oh, so this is a comma over there. I thought it would be 3 continuous equations. That would be not good at all. Yeah. Okay, so these are 3 separate equations. Fine. So what's the thing? Just have minus a x plus b plus c y plus b plus c z, right? That is equal to b minus c. And the next thing you have is c plus a into x plus, is not plus, minus by plus c plus a into z, right, equal to c minus a. And next thing you have is, yeah, just write this out actually, minus a b plus c once again, c plus a minus b c plus a. Why does this look not good? Okay, this is the matrix. And what's the last one? The last one is y equal to, yeah, it would just be a plus b and minus c, and that times x y z, this vector is, what do you have over there? First thing b minus c, next you have c minus a, and then finally you have a minus b. This is bad. This is really bad. How can we make something out of this equation? Okay, fine. So you can always add 2 rows and stuff, but you also have to do the same thing on the right hand side as well, right? Cool. Just like how you solve equations, right? Just like that. Okay, so first of all, we'll try to simplify this. Let's try to add row 1 and row 2. In fact, no, let's add all of these equations together. Let's add all of these together and make that row 1. Add all of these together. A gone but added once again, so it's going to be a plus b plus c, a plus b plus c, a plus b plus c. Yes, x y z. Okay. And the remaining stuff is just, yes, that's correct. You add row 2 to row 1, and then to the new row 1 that you have, you add row 3. It's definitely correct. Yes, this makes sense. Cool. Over there we just have c plus a minus b, c plus a, yeah, something like that, a plus b, a plus b minus c, that is equal to, so you added all of these together on that, it will be 0, it will be 0. So the first equation you can just divide it by a plus b plus c, so that will just give us 1 1 1 everywhere. So there are like some possibilities. The first possibility being that a plus b plus c, they are like all 0. Oh, so you're given that they cannot be 0, so that's fine. Then you can just divide that and this will be 0, uh, c minus a and a minus b. So now once you have this 1 1 1 thing, we can do a lot, we can do a lot of stuff. First thing first, I'm just going to add this thing but multiplied by b to the second row, and that will give us 1 1 1, right? This is a nice representation if nothing else. Add that, so a plus b plus c and 0 and a plus b plus c, and then I will also add plus c over there, so it will be a plus b. I know I'm not supposed to be doing it at the same time, but yeah, it's okay to do that, and it will be 0 over there, okay, times xyz equal to, so first I had to oh, so this is 0 anyway, so we don't have to worry about that, so it will just be 0 c minus a and a minus b, no big deal at all. That's nice, that's really nice. Oh, so we can also do it like this, we can in fact, so because it's 0 nothing matters, nothing matters really, just 1 1 1, yes, 0 minus of a plus b plus c, 0 and then 0 0 minus of a plus b plus c, xyz, that is this thing, 0 c minus a and a minus b. Now you can just take that negative out and stuff, hopefully we can do that. It will just be 1 1 1 0 1 0 0 0 1 xyz equal to 0 a minus c upon a plus b plus c and b minus a upon a plus b plus c. That was really nice. Cool, very nice. Oh, so this equation just becomes x plus y plus z equal to 0, and this this second row is so useful. This just gives us y equal to a minus c upon a plus b plus c, and z, right? What even is this? It's not even, right? It just gave us the answer directly. Fine, cool. And from that you can say x is just negative of their summation, so the sum of these two will be b minus c, so negative of that will be c minus b. Yes, that's how it's supposed to be. Okay, so that's the solution. Oops. Okay, cool. So x is c minus b upon a plus b plus c, y is a minus c upon a plus b plus c, z is b minus a upon a plus b plus c. Nice. Okay, next question. Let this what is this thing? Okay, so consistent, then find the value of r plus s plus t. Okay, that's not nice at all. 3x plus 5y plus 6 equal to. So how am I supposed to solve this? I mean, you could just solve it directly, maybe that would be useful. maybe, right? So two equations, two variables is not that hard to solve. Yes. Just have this thing 2 3 3 5 minus 4 minus 6. Yeah, I'll just multiply this thing by 3, so it will just be 6 and 9, and this will be minus 12 minus 6 3 5. Yeah, that looks correct. And multiplies by 2 as well. Wait, what? That's not correct. That's not correct. Multiply this thing by 3, you just get 6x plus 9y plus 12 equal to 0. Multiply that thing by 2, you just get 6x plus 10y plus 12. Yeah, it's okay, no big deal. So the only thing that it's saying is the y is 0. So y is 0, that means x is minus 2. Yes, so just put that in this, in this. If this is consistent, that means this is gonna work as well. So putting that over there, y equal to 0, so this terms that take cancel, this also gets cancelled. So 2x squared, which means 2 into minus 2, 8 plus 8 into minus 2, minus 16. What else? That's 0, so plus 1 plus t equal to 0. Cool. So t is just 16 minus 9, which would be 7. Okay, find the value of r plus s plus t. The problem with this thing is that r and s, they can be anything. System are consistent. This is not correct. This is going wrong in some way. We know that y has to be 0. So that means r and s can be anything that they want to be, and it will still work. No, this is not nice. This is not correct. R plus s plus t, we don't know. We know that t is 7. T equal to 7. R, S are free. Okay, that is the question that you have. 26. Why? How could you do that? Anyway, let's check this. So first C, yes. Second 0, yes. Third x equal to 1 plus t, y equal to minus 2t, that equal to t. Oh, yeah, I mean it's infinite solutions, but you didn't have to put a parameterization on this thing, right? Or did you? Whatever. I think this is the correct thing to say. It was correct. Infinite solutions. That's what they're saying in this thing as well. T belongs to real. Fourth, all 0. Yes. Fifth, yes, that's correct. And sixth, I don't know what this is. 26th, whatever. Okay, so that's it. I will try this. Okay, so I will do the next thing in the next video. See you later.